All right, so let's keep going. So at the end of like the past lecture, you kind of got the mean, you got the standard deviation. You look at the standard deviation, you're like, what does that number even mean? Like, I got a standard deviation of 2.77 eggs. Like, what does that actually tell me? How do I use that? Like, why is it useful? I'm going to be talking about why the standard deviation is useful right now. Okay, so let's quickly recap. Basically, what we're doing in standard deviation is this measurement of root mean square of deviations from the average. And the standard deviation has the same units as the data. Okay. What I'm going to do now is, instead of using a fake data set on how many eggs I have in my fridge, which I just made up, I'm going to use this data set, which should be pretty familiar to you guys at this point, on baby weights. Okay. So here is, again, the birth weight data, gestational days, maternal smoker, true, false. This should also look familiar to you guys. I forgot to mention this before, but this should also look familiar to you guys because this data was in your midterm as like the histogram question of like smoking baby weights and non-smoking baby weights. So this is a data set that I used. Okay. So what we can do is we can take the histogram of the maternal age. All right. So how many guys think OK, so if you think the mean is bigger, raise your left hand. If you think the median is bigger for this data, raise your right hand. Go ahead. Mean or median? Mean or median is bigger. I'm going to just wave my arms around so you guys can decide. OK, which one's bigger? Mean or median?
Which hand is which?
Huh?
Which hand is
So left hand is mean is bigger. So if you like the mean, right hand is the median is bigger if you like the median. OK, ready, set, go. Try it out. I don't want to give it the answer. All right, so if you raise your left hand, you're doing well. So if you remember, when we try to figure out which one is bigger, we look at the tail, right? Because the tail here has more values that are far away. Those values affect the mean more, right? So here we have some values that are way out over here. That means the mean is going to be more over to the right. The median is going to stay around here. Okay, so the mean is here. The median is like in the middle here. The mean is probably like over out on the right-hand side. Let's take a look. So I can take np.mean. It's like 27, which is like around here. Okay, and the median burst.column 2 is 26, which is pretty close, but a little bit over to the left. Okay. So again, you're never going to find them exactly equal to each other unless your data are perfectly symmetric. In this case, the mean is a little bit bigger than the median because of this tail here. Okay, cool. So I'm going to save these values. I'm going to call this the average equals that. Okay, here's my average. I'm going to take the standard deviation. So I'm not going to do the whole thing again. I'm just going to call it np.std. Okay, so burst.column2, which has the unfortunate acronym of something else. But in this case, I'm going to name the variable SD. So here's the SD. Standard deviation is 5.8. Okay, so it's 5.8. Not really easy to interpret that. But what I can ask you is compare these two things. So take the histogram of, let's say, the weights. So there's a histogram of the birth weights. Here's a histogram of the maternal age. Which one of those has a bigger SD? Okay, and in fact, I think I have a. I don't want to scroll up and down again. Okay, the last time I'm just going to put it on the slide. So there's a slide. Okay, which has a larger standard deviation? Talk it over with your partner.
No, maternal age is more spread out. Yeah, that way it's more spread out. Maternal age then. Which one of us has a larger S?
All right, so okay, so let's try this again. So your left hand, if you think the left histogram, the birth weight has a larger SD, your right hand, if the right histogram has a higher SD, let's see it. Show of hands. What do you guys think? Left or right? So I see rights. I see some lefts. So if you said left, congratulations, you got it right. Now you look at this and you're like, what? Like, what is happening? I thought this has a higher spread. And indeed, usually a histogram like this that has a tail or like a bigger spread will have a higher standard deviation than one like this. But the units here are different. The scale, the x-axis is different here, right? So here the maternal age is like between 20 and 40. So the standard deviation is probably around like 7 or so, around 7 to 10. But here the birth rate goes from like 60 to 180, right, which is a really big difference. And so the standard deviation will also be high to match it. Okay. So it's not just the shape. You have to look at over how much units that the shape is spread out over. Okay. But indeed, if these were at the same units, if I scaled this to the same as this, and the shapes did look like this, then in that case, I would predict that the maternal age histogram does have a higher standard deviation. Okay. So let me just show you that. So I have here birth weight, maternal age. Let's take the standard deviation of those. So let's grab that, np.std, column, do that. So indeed, the birth weight standard deviation is about 18. So here we have here's the mean, right? If I go 18 away, it looks like about this area is a standard deviation. If I take the maternal age, let's take that in there, bam. And indeed, we see that it is 5. Okay, so it is smaller. Even though this looks more spread out, you have to consider the units as well. Okay, so we know that the standard deviation has a measure of spread, but it turns out the standard deviation we can use to actually say, OK, I know for sure that most of my values are within some range. Okay? And we can do that using some mathematics, which I'm not going to outline in this lecture. I'm just going to tell you what it is. So it's called Chebyshev's inequality. What Chebyshev's inequality allows us to do is to say, OK, so no matter what my distribution looks like, whether it's flat, whether it's bell-shaped, whether it's like a U, whether it's some other thing, no matter what the shape of my distribution is, most of my data are going to be in the range like average plus minus a few standard deviations. So that means if I take the average of my distribution and go to the left and right a couple of standard deviations away, so if my average was 10 and my standard deviation was 5, if I go 5 away, and another 5 away, and another 5 away, almost all of my data is going to be within that range. Okay? So it gives us a bound on how much of my data is going to be there. Okay? And this is the bound. No matter what the shape of my distribution, the proportion of values in the range average plus minus z SDs is at least 1 minus 1 over z squared, which is kind of weird. But I can just show you this table. Okay, so the rule of thumb is if I go 2 standard deviations away, I'm going to get 75% of my data, no matter what my distribution is. So even if my distribution is U-shaped, my standard deviation will be high enough that if I go 2 standard deviations away, 75% of my data will be there. Okay, always. You can try this out with any distribution, any data. Yeah.
How does this relationship hold up for one standard distribution, standard deviation?
So if you want to look at this for plus minus 1, so notice I didn't include 1 here. That's because if you go back to this bound and put 1 standard deviation here and calculate 1 over 1 squared, which is 1, 1 minus 1 is 0. So it doesn't have any bounds on 1 standard deviation away, unfortunately. So it says at 1 standard deviation, you're on your own. Who knows what'll be in there. But 2 standard deviations, you're going to get at least 75% of your data, which is pretty good. At 3, you're going to get 88%. And once you get up to 5, you have 96% of your data within there. Yeah, Kevin?
So that means that within 2 standard deviations, you have like 75% of your data on a normal distribution curve.
So you said on a normal distribution curve, this is for any distribution. So I'm going to talk about the normal distribution in a second. But this inequality holds for any shape. Okay? So no matter what, if my data is U, no matter if it's flat, no matter if it's like 1 bar here and 1 bar here, I'm always going to get 75% of my data within that range, average plus minus 2. In the back?
So this is the lower bound, and it's not
That's right. So it's what we would call a lower bound. So we would say at least 75% of my data is in there. I'm going to show you that oftentimes we have more than 75%. This is saying if my data is as spread out as it could possibly be, I'm still going to get 75%, at least 75% in that range, plus minus 2. That was your question. OK, cool. All right, so pretty convenient. Let me show you that is true. Well, let me show you that it works at least on our baby data set. So here is our births. There we go. And what I'm going to do is find out how many fell between plus minus 2 standard deviations in my maternal age column. Okay. So what I'm going to do is take my average, which is the average of this age, take my standard deviation, which was 5 for this column right here. And what I'm going to do is try to find the proportion of rows where the age is in between average plus minus 2 standard deviations, okay? Just to see whether Chebyshev's inequality holds for this data set. So how would I do that? First, where that maternal age column, which is column number 2, is between average minus 2 times standard deviation and average plus 2 times standard deviation. Here I have only the rows where the maternal age fell within that range of 2 standard deviations away from the average. I can find the proportion of rows that are in there by doing num rows divided by the total number of rows in the original table, which is births.numRows. This is long. I'll put it in parentheses. Okay, so put that in parentheses, where just to see it all there. Okay, divided by num rows. There we go. And we see that in this particular data set, 95% of our data fell within average plus minus 2 standard deviations, which is well above the Chebyshev lower bound of 75%. So we find that in a lot of cases we do get over that 75%. But we know that 75% will hold for any shape. Okay. So what I'm going to do now is let's check all the columns. Okay. So births.hist. And if I say overlay equals false, so if I say overlay equals, if I leave it as it is, it'll try to pull all the columns on one histogram, which is not really helpful. I'm going to say overlay equals false to say put them all in separate histograms. And here we go. Okay, so maternal height looks like this. Maternal pregnancy weight looks like that. Maternal age is like that. Birth weight. Maternal smoker is just yes or no, true or false. Here's gestational days. Okay. And what I'm going to do is I have some code here that if I run that, it takes every single column in my births table and looks at the proportion of values within 1 standard deviation, 2 standard deviations, 3 standard deviations, etc. Okay, so it looks like for the first column, which was, if you scroll up, maternal height. Okay, for maternal height, within 1 standard deviation, I got 69%. Within 2 standard deviations, I got 95%. Here's 99%. Okay, so well above my Chebyshev bounds. My Chebyshev bound says there is at least 0% of my data within 1 standard deviation. This is well above. Chebyshev bound says there's at least 75% of my data within 2 standard deviations. We got 95% here. Yeah, Kevin?
The reason why the numbers look like column 0, is that close to normal distribution?
So I haven't covered it, but I will in a second. Okay. So if you're getting excited now, you'll be really excited when I start covering the normal distribution. Okay, so I look at my data and I see, OK, all of these are above my Chebyshev bound. And I think, OK, Chebyshev bound seems pretty good. But I do notice, oddly enough, that all of them are around 0.94, 0.95, 0.97, right? All of them are kind of once I go 2 standard deviations away, I get way more than my Chebyshev bound says I'm going to get. As a bottom line, I get around 95%. And it turns out that that's the case for all of these, from almost all of these. And we're going to figure out if we can get a better bound on, if we can get a better estimation for how many values are within 1 or 2 standard deviations. Okay, I'm giving you the bottom line now, so you can always say, if you walk out on the street and someone asks you how many values are in between 2 standard deviations on my average, you can just say, oh, 75% at least. Okay, no matter what, you don't have to ask the guy what his distribution is. You can just say 75%. Okay, so I'm going to talk now about standard units. Okay, so notice how in these 2 histograms, okay, present that. Notice how in these two histograms, I had different shapes, but also different units. So it's hard to compare them, right? Hard to compare. What we can do is we can change our units to what we call standard units. That gives us a measure that we can use. So instead of saying like, OK, I am 10 eggs away or 30 years away from the average, I can say I am some standard deviations above or below my average. Okay. What we do is we convert our values into this unit called z. And the way we do it is for every value in my data, I'll take that value, subtract away the mean, and divide by a standard deviation. What that means is I'm converting my values. So what I'm doing here is converting all my values to how many standard deviations away from the average they are. Okay. So if my average was 10 and my standard deviation was 2, right? So average 10, standard deviation 2. If I have a value at 12, I'm going to do 12 minus 10, divide by standard deviations. And that value at 12 is what we call 1 standard deviation away from the mean. If I had a value at 13, I do the same calculation, and I get 1.5 standard deviations above the mean. Okay, so what I'm doing here is this z, which is just convention. Okay, so it doesn't really, I don't know if it means anything, but the z there is just what we traditionally use to say standard units. It translates to how many standard deviations away from the average you are. Okay, so if you have a negative z, that means you are below the average. Positive z, you got a value above the average. And if you're at z equals 0, then you have exactly the average of your data. Okay. The convenient thing about converting to standard units is when I convert to standard units, what I'm doing is I'm essentially shifting the histogram over so that it's centered at 0. And then I'm like adjusting the spread of that distribution so that the standard deviation is 1. Okay, which is really convenient. Which means that by Chebyshev's inequality, no matter what distribution I have, most values of z are between -5 and 5, because this is a measure of how many standard deviations away I am. So this is saying most of my values are within 5 standard deviations, plus minus 5 on either side of my average. Okay, let's take a look at that. So I have here the Brits, and I have here. OK, I wasn't supposed to show this yet. Let's pretend it's not there. OK. So what I'm going to do is take my births column. Let's take column number 2 for maternal age. So there are the values in there. What I'm going to do is I'm going to convert them to standard units and then plot them. OK, so you can see what they look like. So I'm going to births, take the average. So I believe the average is still, nope, it got changed. Average is np.mean of that. And the standard deviation is np.standard deviation of that. So here I have average standard deviation, as we've done before. To convert to standard units, I'm going to take, so I'm going to call these my values. Okay. Take my values, subtract out the average, divide by a standard deviation. And here are my values in standard units. So I can make, I'm going to call these my z's. I can make a table that contains these. So with column values, and z, that's my z. Okay. But here are the original values of this maternal age column. And here are the values converted to standard units. So I can plot them on a histogram. I'm going to plot the z-scores. These are what's called the z-scores. So plot those. We see here that we have the same shape as before. So let me plot them both side by side. So here is the original units, right? Standard units. Original units, standard units. The shape is exactly the same. Well, not exactly, right? Because we converted the units here. So the spread is not, it's not as like spread out as it was before. But the shape of the distribution is the same, because all we've done is like moved it over and then like made it spread out so that the standard deviation here is 1. So here, same thing, but in standard units. The average you notice here is 0. And the 1 here is 1 standard deviation away. The -1 is 1 standard deviation away in the opposite direction. Any questions about that? So this is convenient because when we convert to standard units, any distribution in standard units will have an average of 0 and a standard deviation of 1, which means that if I take this, if I take this and do the same thing on, let's say, my birth weight column, even though originally the birth weight column is in like 120, 113 range, around there, if I convert to standard units, it'll have an average of 0 and a standard deviation of 1. That lets me compare the two distributions and say, OK, which one do I think has a higher standard deviation or not? Okay, so I encourage you to try it out on your own. You can try to see, OK, based on my standard units, can I work backwards? Can I get back? Can I draw some conclusions about my data or what my data, the shape of my data are if I convert to standard units? Cool. And now we are ready to talk about attendance. Let's do attendance first. Go, resume that. Bam. Go ahead. And there's me. I love data. Here's a link. OK, so now we're finally ready to talk about what we call the normal distribution. Now in this class, we've done a bunch of like manipulation of data, simulations of data, and you've seen this shape appear a lot, where it's like it's a nice bell curve. It goes up and then down, right? And it seems odd that it appears so often in like very different circumstances. And it turns out that that shape has a name. It's what we call a normal distribution. Okay. Now, normally, it's not very easy to say what the SD is by looking at a histogram. So especially if my histogram is an odd shape, so if it's like a U, it's like really hard. I'm really not super sure what my standard deviation should be, unless my histogram has a bell shape. Okay. So it turns out that if it is in a bell shape, it is relatively easy to estimate that standard deviation. Let me just show you how. So go there. OK. It's the same thing. And that. So here is the maternal height plotted on a histogram. You can see that in this case, the height happens to have kind of a bell shape, so which means that it starts low and then goes up and then goes back down. It doesn't go back up again. It's not like waves. It's just one up and then one down. When we see this, we can say, OK, we think the standard deviation is where we think the inflection points of this curve are. So by inflection points, I mean, OK, so here, the slope is going up, the slope is going up, the slope is going up. And then right here, the slope is going down. It starts to curve downwards, right? So it goes from curving upwards to curving downwards. And the point at which it starts curving, or it changes direction of curvature, is the standard deviation. Okay, so right here, it looks like around like here is where I expect the standard deviation to be, which means that if I take this point here, subtract it away from the average, which is 64, this right here is about what I think the standard deviation is, which looks like it's about 3. Let's try it out. Hopefully I'm not way off. Grab that. that. Column 3. And indeed, it's about like 2.5, so kind of close. Okay. Now, we call this shape roughly normal. And that's because a normal distribution has a theoretical shape that looks something like this. Okay. So what I'm going to do here is I'm just going to call like, okay, go to the NP.random and grab samples according to a very like precise mathematical normal distribution. So there's a theoretical normal distribution that looks like this. Okay. So the theoretical normal, I'm going to let that run for a little bit, looks like this, which is really, really nice, symmetric, bell-shaped, all that stuff. Okay. This is the theoretical normal distribution. And in practice, we get stuff that looks kind of close, but probably not exactly the same. Okay. But if we say that if the shape looks kind of like this, or if it's close enough, then we call this like roughly normal, depending on what we're looking at. Okay. Now, what's the importance of normal? It turns out that, okay, so let me go back to here. Is anyone still taking attendance? We're good? All right, done. So it turns out, as I mentioned, if my histogram is bell-shaped, then I look at my average, and I go from the average to an inflection point that lets me roughly estimate the standard deviation just at a glance. Okay. Now, if our data are normal, so we know that even if our data are not like bell-shaped or whatever, we know that because of Chebyshev's inequality, that most of our data are in the range average plus minus a few standard deviations. Okay. But if our data are normal, we can tighten those bounds a little bit, and we can say almost all the data are in the range average plus minus 3 standard deviations. Okay. So it turns out that if you go through and work out, given the normal distribution, like a theoretical normal, work out how many values are in between 1 standard deviation, 2 standard deviations, we get this. Okay. So this is Chebyshev's, which says that at least 0% of my data are within 1 standard deviation, at least 75% are within 2. But if we happen to know that our data, are perfectly normal, then we can say about 68% are within 1 standard deviation, about 95% are within 2. That 95% looks suspiciously like what we did before, right? So if I go back, we look to here, this is almost 95%. So for a lot of these, we look at, so again, we can look here and say, okay, it looks like this one is pretty normal, like bell-shaped. This one maybe not so much. This one maybe not so much. But this one looks pretty nice, symmetric, right? This one, no. But this one, probably yes. And if you look at the standard deviations and look at how many values fall in between, you'll notice that in our case, they're like mostly around 95%. Some of them are below. So when our distribution is not perfectly bell-shaped, we won't get exactly 95%. We'll get a little bit lower. Okay? But if it is perfectly bell-shaped, then within 2 standard deviations, we'll get exactly 95. Here we have a little bit more. So again, our real data will not be perfectly bell-shaped, but knowing the normal distribution and the bounds there will help you give you some idea of like, okay, I can expect most of my values to be within 2 or 3 standard deviations away. So better bounds than the Chebyshev inequality. They're not precise. Like I can't say it's always going to be lower or it's always going to be higher than anything, but it lets me estimate at a glance. Okay, cool. All right, so now we're ready to talk about why we see that bell-shaped curve pop up so much. All right, so for that, these numbers are just good to know. As always, like you never know when someone will ask you on the street, oh, I have a normal shaped curve. How many values are in between 2 standard deviations? You'll never know when that comes in handy to say 95%. Okay, so you should probably, so you know the memory this is definitely going to be like at least 0, at least 75. And a normal distribution is around that number. If it's normal, I can get better estimations for what I think it is. Yeah, Kevin? Yeah, so in this case, this table was made for like, if my data look roughly normal, then it is about 95. If my data are precisely normal, somehow, then it will be 95. But even if I were to do that simulation again with the np.random.normal and like draw that theoretical normal curve, because I'm doing random sampling there, I'm still not going to get precisely 95%. It's only 95% if I take that equation for like the smooth normal curve line and then find how many are 2 standard deviations away. So basically, in almost every single case that we'll work with, especially in this class when we're working with real data, it will be about these numbers if the data are normal. Cool. So this leads me to a cool little result, which is called the central limit theorem. Okay? And what this says is if my sample is large and drawn at random with replacement, then regardless of the distribution of the population, if I take samples and get the probability distribution of my sample sum or my sample average, that will be roughly bell-shaped, which is kind of interesting. Okay, let me show you what that means. Okay, so if I have, I'll grab my notes. So let's take a look at the histogram of maternal age again. So here it is. Maternal age, the distribution looks like this. So this is not really bell-shaped. It has like a pretty long tail here, right? But if I were to draw some samples, so first let me grab the average of this just to show you. So here I have np.mean, column 2, go. But again, the average is 27.2. If I were to sample that, let's grab a sample and grab column 2 and take the mean of that again. So mean. So here I'm grabbing a sample of the same size as my original and taking the mean. Now we know that if our sample is large enough, we expect that the sample mean be equal to the population mean or be pretty close to the population mean, right? So our sample is relatively large compared to our population. So when we grab a sample, that sample mean is pretty close to that population mean. Now watch this. So the population distribution of ages goes up and it has a long left tail here, right? But if I take a bunch of samples, take the means, and then plot the means, you'll see this. Okay, so grab my means for I, and let's do 1,000 repetitions, 10,000. Let me just grab this means.append, put that in there. So I'm grabbing a bunch of means. And let's take those means. Okay, so here are my means. I'm going to plot them in a histogram. So column, mean. Just going to chug along. There you go. So we have a bunch of means because I sampled from my population 10,000 times. I'm going to clear that because that's really big. Clear it. Plot them on a histogram. Lo and behold, even though my population distribution of my ages looked like it had a left tail, when I grabbed samples and took the sample mean of every sample and plotted those samples on a histogram, this histogram is normal. And this is an interesting result from statistics called the central limit theorem, which basically says, as my sample size increases, this is going to look more and more normal. Okay, so if I were to redo this, let's say I redo this, let me lower this so it runs faster. Redo with a sample of size 10, and that it's like kind of spiky. You can kind of see a symmetric. If I do this with size 100, let's try that. Let me not display that. Let me do means. Just show the first 5 elements. Okay, it's looking a little bit nicer, right? If I keep increasing the sample size, then it looks more and more normal. And that's what the central limit theorem tells us. Okay. Now you look at that and you're like, why? Well, how could that happen? And unfortunately, I won't tell you why. You have to take more stats classes to find out. But if you want an idea for why, so the reason that, for example, when you look at people, and when you look at the heights of people, you'll often find that if you grab a sample of people and take the heights and plot them, that the heights are bell-shaped, right? And that has an interesting, and the reason why that happens, and the reason why it's bell-shaped there is because it's not super related to the central limit theorem, but the reason why we see bell shapes occur oftentimes is because if you look at a person's height and just think about genetics, right? So there's some genes that when you flip them on, they'll like add some to your height. So if you have like, maybe there's like 100 height genes, I don't know how many there are, but there are a bunch of genes that affect your height. If you flip, let's just pretend for instance, that every single gene, if you flip it on, will give you like 1 extra inch of height. Okay? Flip it on, you get 1 extra inch of height. So if you have 100 genes, you flip them all on, you'll become like 7-foot Yao Ming. If you flip them all off, you'll become like really short, like Hobbit. Okay? And most people, about half of them are flipped on and off, right? So if you flip half of them on and off, you get like an average height. But if you were to pretend like each one of them can be flipped on and off with some probability and model that, what you'll get is a normal distribution. Okay, so if you were to try it out, if you want to try it, you can try it out in the notebook, do a simulation, show that distribution of heights. You'll find that you'll actually get that bell shape just by doing that simulation. And it comes about because of interesting results of probability. One of the reasons is if you have something like that where like you have a bunch of small factors that eventually affect or add up to something else, you're going to get that bell shape. Another reason why you get the bell shape is because of the central limit theorem. So that's why like when we take the bootstrap and we sample the means, or the bootstrap and we sample the medians, for example, we get that nice bell shape. So it just so happens that oftentimes we observe the bell shape just because of interesting statistical effects that you can learn about in a future stats class. Yes, Kevin?
Is there any similarity between the central limit theorem and the law of averages?
Okay, so typically, law of averages, what are you referring to?
With like approaching the normal distribution, approaching the probability distribution.
I believe there is some relationship there, but we're not going to go into that in this class. And for our purposes, it's just important to know that if we take large samples, then the distribution of our sample means will be roughly normal, which is very convenient. It's what allows that bootstrap. So you remember from the bootstrap, we had some criteria for when you couldn't use a bootstrap, right? One of those criteria is when the sampling distribution of your statistic is not like roughly bell-shaped, and that's because that's the case when the central limit theorem does not hold. When your sample is either too small or you're looking at some statistic that's way out there, like the 99th percentile or 95th percentile. But if you look at the mean, so the reason why we can do this for the mean and the median at will when you do the bootstrap is because the central limit theorem says, as we take bigger samples, we're going to get something that's roughly normal. Very convenient. And that's it. We ended 30 minutes early. I'll see you. Have a good weekend.